Electromagnetic Induction Applied to Agriculture, narrated by Rick Taylor. This presentation is intended to introduce professionals in agriculture to the geophysical technique of electromagnetic induction. Low-frequency electromagnetic fields provide the basis for electromagnetic induction, in contrast to electromagnetic radiation that uses high-frequency electromagnetic waves. Electromagnetic induction provides a convenient way to map and sound electrical conductivity to depths of interest in agriculture. The presentation shows research by parties independent of Dualem Inc. as examples of electromagnetic induction application. Any citation of the examples should give proper acknowledgement to the original sources. The presentation summarizes electromagnetic induction techniques used to measure electrical conductivity, reviews the conductive characteristics of agricultural materials, shows how several researchers have applied electromagnetic induction to agriculture, discusses the quantitative limits of measurement with current instrumentation, and lists the references used. The term near-surface invites definition by depth. From the perspective of academic geophysics, which considers the Earth to its core, or petroleum geophysics, which searches beyond 10 kilometers, 1 kilometer is near surface. Electromagnetic induction techniques with large transmitters can sound to 1 kilometer. Large transmitters consisting of loops of wire enclosing several hectares or more are customary with the time domain technique, in which the transmitter pulses and then is off during measurement. Time domain and transient are synonymous. Mobile coils to transmit and receive electromagnetic fields enable much faster surveying of an area with finer spatial resolution, but less depth of exploration. Frequency domain transmitters operate continuously, and this relative efficiency makes them better suited to small size. The frequency domain technique measures response over a spectrum ranging typically from several hundred Hz to tens of kilohertz. Practical limits of both time domain and frequency domain techniques make them generally unable to resolve conductivity in the uppermost few meters of the Earth. The geometric technique uses a transmitter that operates continuously at a frequency that is sufficiently low that response is independent of frequency. Response depends solely on the geometry of the transmitter-receiver array and the layering of conductivity beneath the array. The technique is unique in its ability to resolve shallow conductivity when used with arrays up to 6 meters in length. The electromagnetic induction transmitter coil creates a sinusoidal primary magnetic field. Where the field meets conductive material, such as in the Earth, it induces sinusoidal electrical current. In geometric electromagnetic induction, the level of induction in the Earth is sufficiently low that all electrical current can be considered to flow parallel to the Earth's surface, which facilitates the interpretation of the depth of response. The induced current creates a secondary magnetic field. When the secondary field intersects the receiver coil of the electromagnetic induction array, it induces current in the coil. This response, measured by the coil, is quantified by amplitude and phase relative to the amplitude and phase of the primary field at the receiver coil. For geometric electromagnetic induction, the amplitude of the secondary field at the receiver is typically a few parts per million to several parts per thousand of the primary field. The phase of the secondary field is essentially shifted by 90 degrees, that is, in quadrature, relative to the primary field. Typically with geometric electromagnetic induction, the amplitude of quadrature response is scaled linearly to apparent electrical conductivity in units of millisiemens per meter. Synonyms for geometric domain in geophysical literature are low induction number, low frequency approximation, and resistive limit. In general, electromagnetic response is a complex function of system frequency, array geometry, and the spatial distribution of electrical conductivity and magnetic susceptibility in the Earth. In the geometric domain, response is linearly proportional to the conductivity of the material within the sampling volume of the array. The dimensions of the sampling volume, such as the depth of exploration, are linearly proportional to the length of the array and independent of frequency, conductivity, etc. The sensitivity of an array to a given range of depth in the sampling volume is defined by a simple function. The response of a layer that occupies a given depth range is the product of the conductivity of the layer and the value of the sensitivity function. Total response is the sum of the layer responses. These characteristics of geometric electromagnetic induction make interpretation of response simple and robust. Where responses of several arrays are available, estimates can be made of the conductivity, depth, and thickness of conductive layering. The depths of exploration of arrays used in geometric electromagnetic induction range from 0.5 to 1.6 array lengths. Thus, arrays of about 1 meter length are sensitive to depths of interest to agriculture. Geometric electromagnetic induction response to conductivity is essentially in quadrature relative to the transmitted field. The response to magnetic susceptibility is in phase with the transmitted field. Thus, instrumentation typically used in geometric electromagnetic induction separates these responses that are confounded in frequency and time domain electromagnetic induction. The transmitter and receiver in geometric electromagnetic induction instrumentation are coils of wire wound circumferentially about an axis. The coils are separated by at least several coil diameters, so each can be treated mathematically as an oscillating magnetic dipole coincident with its axis. At-surface geometric electromagnetic induction typically uses arrays of 3 geometries of given length. They are, firstly, the horizontal coplanar array, which has horizontal coplanar coils. Vertical dipole is another term for this array, but horizontal coplanar is prevalent in the geophysical literature. Other arrays also have vertical dipoles, for example the induction Auger coaxial array, but different sensitivities. The depth of exploration of the horizontal coplanar array is 1.6 array lengths. Secondly, the perpendicular array, which has a horizontal coil and a vertical coil, where the axes of the coils intersect each other. The depth of exploration of the perpendicular array is 0.5 array lengths. Thirdly, the vertical coplanar array, which has vertical coplanar coils. Horizontal dipole is another term for this array, but there is also a coaxial array with horizontal dipoles. The depth of exploration of the vertical coplanar array is 0.75 array lengths. Depth of exploration is the term to which an array accumulates 70% of its full sensitivity to conductivity. A similar term is depth of investigation, the depth to which an array accumulates 50% of its full sensitivity. The arrays of geometric electromagnetic induction instruments used for agriculture operate at various frequencies from about 0.4 to 20 kHz and are usually 2 meters or less in length. Increasing frequency decreases the conductivity limit of the geometric domain, but by less than a proportional increase in array length. The present comparison assumes a frequency of 9 kHz. Conductivity in agricultural materials reflects a mixture of the conductivities of two main constituents. Firstly, pore space moisture, and secondly, texture if the material is a soil. Fresh moisture, as might be found in a lake with low dissolved solids, might have conductivity less than 10 millisiemens per meter. The conductivity of the superficial ocean is about 3,000 millisiemens per meter, and saline soil might have conductivity greater than 200 millisiemens per meter. Dry, coarse soil might have conductivity less than 1 millisiemen per meter. Soil of low activity clay might have conductivity as low as a few millisiemens per meter, while the conductivity of soils of high activity clays might be over 100 millisiemens per meter. The shorter perpendicular arrays measure geometric domain conductivity for all materials of agricultural interest. Exceptions for the 1 meter horizontal planar array might be saline soils and wastes. The most conductive soils are an additional exception for the 2 meter horizontal planar array. Noise of about 1 millisiemen per meter limits measurement accuracy for poorly conductive materials. The senior application of electromagnetic induction in the uppermost 10 meters is mapping the extent of superficial materials that contrast in electrical conductivity or magnetic susceptibility. Geometric domain instrumentation can also locate metallic debris, disused utilities, and archaeological zones that might occur in agricultural areas. Following theoretical development in the 1960s, we have developed instrumentation and techniques for sounding conductivity to several distinct depths. The robust interpretability of these soundings, where the Earth has conductive layering, allows the estimation of layer conductivity and the depth to layer interfaces. More recent improvement in the stability of instruments has made possible the monitoring of changes in the extent, depth, and conductivity of dynamic features, such as contaminant plumes and saline horizons. For conductive features that are related to agricultural inputs and wastes, delineating their boundaries and monitoring changes in their extent and contrast can support agricultural management. Assessing and monitoring soil salinity is a mapping application in Mediterranean and other regions where high-value agriculture coincides with conditions that are periodically hot and dry. Here, Verdano et al. Used 1 meter perpendicular apparent conductivity to map a basin in northeastern Spain that is undergoing development for irrigation. The survey determined that much of the area has apparent conductivity less than 20 millisiemens per meter, but a few areas of high conductivity are potential sources of salinity. Additionally, there seems to be some salinization of drainages. The researchers divided the basin into watersheds and sampled the conductivity of drain water at the watershed exits. Verdano and associates compared drain water conductivity to the average apparent conductivity measured in the corresponding watershed and found reasonable correlation. A couple of outliers had relatively high watershed conductivity but low drain water conductivity. These were from 2 watersheds where a cross-cutting canal may be leaking irrigation water into drainages. Future surveys of geometric electromagnetic induction are planned to help analyze salinity trends and assess consequences of irrigation. The setting of a sounding example is a 2-hectare site in Flanders, about 60 kilometers from the North Sea. In this region, Loess overlies marine clay. Previous sampling in the region indicates that the Loess cover can be thin to several meters thick, but its typical thickness is about 1 meter. Say et al. measured quadruple apparent conductivities with 1 meter horizontal coplanar, 1 meter perpendicular, 2 meter horizontal coplanar, and 2 meter perpendicular arrays at over 10,000 locations within the site. At each location, the 4 apparent conductivities were used to estimate loess conductivity, loess thickness, and clay conductivity. The best fit models to the measurements yield a range of 3 to 31 millisiemens per meter for loess conductivity, 0.09 to 4.9 meters for loess thickness, and 85 to 171 millisiemens per meter for clay conductivity. At 24 locations, the thickness estimates were checked by augering. The model estimates of thickness and the depth observations at the auger sites agree reasonably well. Electromagnetic induction has traditionally been used to map the lateral extent of contrasting soils. This example shows its capability in sounding the buried interface as well. In a monitoring application, Eigenberg et al. Show periodic surveys during the growing season can indicate changes in soil and crop status. After an application of fertilizer in late March, an increase in apparent conductivity seems to have accompanied increases in soil moisture and dissolved nitrate through the spring. Fertilizer was applied again in June, but apparent conductivity dropped about 40 millisiemens per meter with soil moisture as the corn crop grew rapidly from 30 centimeter height. Although moisture recovered through July and August, apparent conductivity remained relatively low along with dissolved nitrate during the maturation of the crop. Monitoring of conductivity throughout the growing season might suggest areas and times for the adjustment of moisture and dissolved nutrients for optimum yield. The management of productive sites demands the integration of diverse information in ways that might be specific to the site or crop. For the corn crop of Eigenberg and Associates, we find that apparent conductivity would be an effective measure of combined moisture and dissolved nitrate through the year, allowing for a scaling factor and a constant. In general, electromagnetic induction can provide spatially comprehensive information about soil texture and temporally consistent monitoring of moisture, nutrients, salinity, and waste. Researchers and consultants have identified a variety of relationships that may have some breadth of application. The value of application at a given site is certain to have site-specific boundaries, but it seems that frequent surveying using arrays that provide a range of depth sensitivities is essential to assessing the potential benefits of electromagnetic induction. Gilly et al. Used a 1 meter perpendicular array to map cattle pens. An area in this pen near both the feed bunk and water tank has an apparent conductivity of about 300 millisiemens per meter. Its surface contained relatively abundant compacted waste. A secondary area of elevated conductivity extends from a windbreak to the northern edge of the pen. Simulated rainfall was applied to test areas in the upper, middle, and lower slope areas of the pen. Runoff was captured and chemically analyzed. When constituent concentrations were compared to the apparent conductivity of the test areas, ammonium shows the greatest correlation, followed by electrical conductivity and dissolved phosphorus, then by chlorides and pH. The example shows that apparent conductivity can indicate the distribution of waste within an animal pen, and that apparent conductivity is correlated to some constituents of the waste that might require management. Mapping, sounding, and monitoring applications that require absolute accuracy of a few millisiemens per meter are possible with the best available sensors that have such accuracy and provide a rich set of apparent conductivities that sample to multiple depths. Since electromagnetic instruments are sensitive to metal, the sensor should be placed far enough from any metal, for example of a towing vehicle, to make noise from the metal negligible. This distance is usually an array length or more. In general, measurements should be made as close as practical to the surface to maximize response amplitude. Zero-level drift in sensors arises primarily from imperfect compensation for thermal distortion of the sensor housing and thermal characteristics of array components. For applications that require the greatest absolute accuracy, the sensor should be allowed to stabilize with power on at ambient temperature and shaded from direct or fluctuating sunlight. Vertical sounding is a practical way to check zero-level calibration, as well as to obtain data for detailed analysis of conductive layering. If feasible, measurements should be made at heights up to twice the array length. Illustrated here is a non-conductive apparatus for raising longer sensors to substantial height. The accuracy of measurements determines the limits of quantitative interpretation of conductivity and layering in the near surface. Assuming a noise envelope of 1 millisiemens per meter, it is generally impractical to consistently trace or delineate features with less than 5 millisiemens per meter contrast with adjacent material. The growing season example suggests that higher contrast, to overcome temporal as well as spatial variability, is required for monitoring applications. Perhaps the monitored feature should provide contrast or dynamic range of at least 10 millisiemens per meter. The horizontal coplanar array has the greatest depth sensitivity of any array used in near-surface electromagnetic induction instruments. Its sensitivity function suggests that near-surface electromagnetic induction, as described herein, is limited to a depth equivalent of about 2 array lengths. The Loess over clay sounding example supports this guideline. Using 4 arrays, of which the deepest sensing was a 2-meter horizontal coplanar array, Say and Associates estimated depths as great as 5 meters. Note that, in this case, the underlying clay was roughly an order of magnitude more conductive than the Loess. As the contrast and layer conductivity decreases, estimates of depth and conductivity will be less definitive. The preceding examples show that near-surface electromagnetic induction can address a wide range of situations of interest to agriculture, hydrogeology, and environmental monitoring. In addition to mapping and sounding the distribution of materials at contrast and conductivity, electromagnetic induction can monitor changes in factors essential to agricultural productivity and waste management. The range of application and reliability of results depend to a large degree on the quality of instrumentation, the care taken in data acquisition, and the suitability of the interpretational technique. To recap the references that provided the material for this presentation, Eigenberg et al. Monitored conductivity through the growing season and showed its relationship to moisture and dissolved nitrate. Gilly et al. Mapped waste distribution in a cattle pen and correlated some waste constituents to apparent conductivity. Say et al. Modeled the conductivities and depth of Loess over clay. Giordano et al. Mapped a basin for salinity and correlated rainwater electrical conductivity to watershed apparent conductivity. Supplementary material can be found at the Dualem website. Thank you for viewing this presentation.